Today, we are going inside the factory. We are following copper and aluminum from raw material to finished product, tracing the invisible science of heat, and discovering why the companies that master thermal engineering are the ones quietly shaping the future of computing. Let us begin at the beginning, not with a product, but with a problem. Heat is the oldest enemy of electronics. Since the very first transistors were assembled in laboratories in the late 1940s, engineers have understood that electricity and heat are inseparable companions. Every calculation your processor makes, every frame your graphics card renders, every byte your memory retrieves, all of it generates thermal energy. And thermal energy, left unchecked, destroys precision silicon the way prolonged drought destroys farmland, slowly, silently, and without mercy. Modern processors operate at temperatures that would have seemed catastrophic to engineers just 2 decades ago. High-performance gaming chips routinely push past 100 degrees Celsius under full load. At those temperatures, silicon begins to throttle its own performance, deliberately slowing itself down to avoid permanent damage. The machine protects itself by becoming less of what you bought it to be. The solution to this problem has evolved over decades, from simple aluminum heat sinks to complex liquid cooling systems. But somewhere in the middle of that evolution sits a technology that is elegant in its simplicity and astonishing in its efficiency: the heat pipe. Deepcool, founded in Beijing and operating advanced manufacturing facilities in Huizhou, China, has built its identity around mastering this technology at scale. The company's mission is not simply to make cooling products. It is to engineer thermal consistency for the most extreme workloads that modern computing can generate. Every production line, every quality checkpoint, every material choice reflects that singular purpose. The story of how a Deepcool cooler is made begins not with metal or machinery, but with a philosophy. Precision must be repeatable, efficiency must be measurable, and every product that leaves the factory must perform identically to the one before it and the one after it. In a world where a single failing cooler can destroy a processor worth several $100s, consistency is not a virtue, it is a survival requirement. The foundation of Deepcool's thermal engineering is the heat pipe, and understanding how a heat pipe works unlocks everything else that follows. A heat pipe is, at its core, a sealed copper tube. Inside that tube lives a small amount of purified liquid, typically water, and a porous internal structure called a wick. When one end of the pipe, the end touching the hot processor, absorbs heat, the liquid inside vaporizes almost instantly. That vapor travels at extraordinary speed through the interior of the tube toward the cooler end, where it condenses back into liquid. The wick then draws the condensed liquid back toward the hot end through capillary action, the same natural force that pulls water up through the roots of a tree. The cycle repeats continuously, silently, and without any moving parts whatsoever. This process is so efficient that a single copper heat pipe can transfer heat several thousand times more effectively than a solid copper rod of the same size. The physics were understood long before the technology became affordable to manufacture. It took decades of materials science, precision tooling, and industrial engineering before heat pipes could be mass-produced with the consistency that consumer electronics demand. The journey of each heat pipe at Deepcool's facility begins with copper tubing prepared for internal transformation. The tubes are cleaned, shaped, and loaded with precisely measured quantities of copper powder. That powder must be distributed with extraordinary evenness across the interior surface, because any irregularity in distribution creates irregularity in thermal performance. Once the powder is placed, the tubes are sealed under vacuum. The absence of air is not incidental. It is essential. Even trace amounts of oxygen or nitrogen inside a heat pipe can degrade performance and accelerate internal corrosion over time. This initial preparation phase is invisible to the consumer who eventually installs the cooler in their system. But it is arguably the most critical stage in the entire manufacturing process. Like the foundation of a building, it determines the structural integrity of everything built on top of it. Once the copper powder is in place and the tubes are sealed, the pipes enter a sintering furnace. Sintering is a process borrowed from metallurgy and ceramics, used for centuries in various forms but perfected for modern engineering, applications only in the last half of the 20th century. In sintering, the copper powder inside the tube is heated to temperatures approaching the melting point of copper without actually melting it. The particles bond at their contact points, fusing into a continuous porous matrix while retaining the small air gaps that make capillary action possible. The result is a structure that resembles, at the microscopic level, a sponge made of copper. It is rigid, thermally conductive, and precisely engineered to move liquid through itself in a single preferred direction. Guide rods inserted during the process to maintain the internal channel geometry are removed after sintering, leaving behind the hollow center through which vapor will eventually travel. What emerges from the furnace looks nearly identical to what went in, but it is fundamentally molecularly different. With the internal structure formed, the heat pipes move to sealing and purification. Laser sealing closes each tube with a bond that is airtight at the molecular level. This is not the kind of sealing you do with adhesive or compression fittings. Laser welding fuses the copper itself, creating a continuous metal surface with no joint, no gap, and no potential failure point. Following the seal, each tube undergoes hydrogen annealing, a heat treatment process conducted in a hydrogen-rich atmosphere that removes residual stress from the copper and eliminates microscopic surface impurities. The hydrogen reacts with and removes oxygen compounds from the copper surface, a process that has been used in precision metallurgy for over a century. Then comes the water. Purified water, measured in quantities precise enough to affect performance if miscalculated by even a fraction of a milliliter, is introduced into each tube before final sealing. That water will become the thermal working fluid that carries heat for the entire lifespan of the product. The quality of that water, its purity, its quantity, its interaction with the internal copper structure, is what separates a heat pipe that lasts a decade from one that degrades in 2 years. Accelerated aging tests subject finished pipes to thermal cycling far beyond anything a typical computer workload would produce. The goal is to simulate years of use in a matter of days, exposing any internal weakness before the product ever reaches a consumer. Once the pipes survive thermal validation, precision shaping begins. Computer-controlled bending machines guide each pipe through the curves and angles that allow it to fit within the complex geometry of a finished cooler. Heat pipes cannot be bent freehand. The internal wick structure is sensitive to compression, and a bend executed with even slightly too much force in the wrong direction can collapse the internal channel and destroy the pipe's ability to move fluid. The machines that perform this bending are calibrated to tolerances measured in fractions of a millimeter. After bending, calibration pressing flattens the sections of pipe that will contact the processor surface. A flat contact surface maximizes the area through which heat enters the pipe, and even microscopic gaps between the pipe and the heat source represent thermal resistance that costs performance. Each pipe is then tested individually, its thermal transfer rate verified against specification before it is cleared for assembly. This individual testing represents an investment of time and cost that many manufacturers skip in favor of batch sampling. Deepcool's approach treats each pipe as its own product, accountable to its own performance standard. The aluminum fins that surround the heat pipes in a finished cooler are manufactured separately through a process of stamping and surface treatment. Sheet aluminum is fed through high-precision dies that stamp out fin shapes by the thousands. The texture pressed into each fin is not decorative. Surface texture increases the effective area available for heat exchange with passing air, a principle that engineers call augmented surface area. A textured fin can transfer significantly more heat than a smooth fin of identical size because it creates more contact points between the metal and the airflow moving through it. Once stamped and textured, the fins are threaded onto arrays of aligned heat pipes by robotic assembly systems. The tolerances required for this step are genuinely beyond consistent human capability. Each fin must sit at precisely the correct spacing, with precisely the correct contact pressure against the pipes. Too loose and thermal transfer between pipe and fin is compromised. Too tight and the fins deform, disrupting the airflow channels between them. The robots that perform this assembly are calibrated to maintain these tolerances across thousands of units per day, achieving consistency that no human-operated line could match at scale. In the most demanding coolers in Deepcool's lineup, vapor chambers enter the design alongside heat pipes, and the combination represents the current frontier of consumer thermal engineering. A vapor chamber is in concept a flat version of a heat pipe. It contains the same internal wick structure and the same phase change working fluid. But where a heat pipe transfers heat in a single direction along its length, a vapor chamber spreads heat in 2 dimensions simultaneously, distributing thermal energy across its entire surface area almost instantly. This makes vapor chambers particularly effective for modern processors. which generate intense localized heat across a die that may span less than 2 square centimeters. Pairing vapor chambers with heat pipes creates a system where heat is first spread laterally across the chamber and then transported vertically through the pipes into the fin array. The alignment and soldering processes that bond these components together are conducted in nitrogen-protected environments to prevent oxidation during the brief window when metal surfaces are exposed and reactive. The resulting joints operate at the molecular level, with bonding quality that directly determines how efficiently heat moves from one component to the other. No discussion of a CPU cooler is complete without addressing the fans that move air through the fin array, because the most thermally perfect heatsink in the world is useless without airflow. Deepcool's fan engineering begins with motor winding, the process of coiling copper wire around magnetic poles to create the electromagnetic field that drives blade rotation. The precision of this winding determines the smoothness of motor operation, and motor irregularities are the primary source of acoustic vibration in cooling fans. Each motor is tested for rotational stability and electrical balance before blade assemblies are attached. The fan blades themselves are the product of extensive fluid dynamics analysis. Their curvature, angle, and surface profile determine how efficiently they accelerate air through the fin array rather than simply displacing it. Acoustic testing of completed fan assemblies is conducted in anechoic chambers, rooms lined with sound-absorbing material that eliminate all external noise, allowing engineers to isolate the specific frequency signatures produced by each fan design. The goal is not just to reduce total noise level, but to tune the acoustic profile of the fan so that the sound it does produce is within the frequency range that human hearing finds least intrusive. Final assembly brings every component together: the heat pipe and vapor chamber structure, the fin array, and the fan assembly. Once assembled, each unit is subjected to thermal simulation testing that replicates real-world processor workloads. The cooler is mounted on a calibrated heat source, the system is driven to full load, and temperature readings across multiple points are recorded and compared against specification. A unit that fails to maintain target temperatures at any measurement point does not proceed to packaging. Anechoic chamber testing of the complete assembly adds a human dimension to the measurement process. Instruments measure decibel levels and frequency spectra. But trained engineers also listen, because the human auditory system is sensitive to qualities of sound, harmonic resonance, directional character, intermittent variation that instruments do not always capture completely. The combination of objective measurement and subjective evaluation is the standard by which the final acoustic performance of each model is certified. The last steps before shipping, thermal paste application and protective packaging, are treated with the same seriousness as every step before them. Thermal paste is applied to the heatsink base in patterns optimized to spread evenly under mounting pressure, filling the microscopic surface irregularities between the cooler and the processor lid. The pattern and quantity of paste matters more than most consumers realize. Too little leaves thermal gaps. Too much creates an insulating layer of excess paste at the edges. The application process is calibrated to achieve a specific coverage area under a specific mounting force. Accounting for the typical surface geometry of the processors, the cooler is designed to support. Packaging materials are selected for anti-static properties and moisture resistance, protecting a precisely engineered product during a journey that may involve multiple climate zones, varied humidity levels, and the mechanical stresses of international shipping. The cooler that arrives at a consumer's door is, in all measurable ways, identical to the cooler that passed final inspection on the factory floor. Here is what this story really teaches us. Excellence is not a destination. It is a system. Every stage of this manufacturing process exists because someone, somewhere, identified a specific failure mode, a performance gap, a quality inconsistency, and engineered a solution for it. The result is not perfection through inspiration. It is perfection through discipline, repetition, and relentless attention to things that most people never see. That principle applies well beyond cooling technology. In your own work, in your own craft, whatever it may be, the invisible steps are usually the most important ones. The preparation nobody watches, the testing nobody applauds, the attention to detail that never appears in a finished product is marketing material but determines whether that product succeeds or fails. Ask yourself this. What are the invisible steps in what you do? Are you doing them with the same seriousness that this manufacturing process demands? Because the gap between good and extraordinary almost always lives in the spaces that no one else bothers to look. If this kind of content adds value to how you think, subscribe to the channel. There's always more to explore and the next story is already waiting.